begin. Last time, we continued considering set equivalence. You know, two sets are equivalent. When are they equivalent? Two sets are called equivalent if and only if.
There is some bijection between them.
Yeah, there is a bijection or one-to-one correspondence, which are synonyms. There is a bijection from A to B. There is a function from A to B, which is a bijection. So, we know some facts about these bijections. For example, what do we know? We know that n squared, the set of all pairs of natural numbers, is equivalent to what?
To set of naturals.
Yes, just to n. We know that, say, A times B is equivalent to what?
To B times A.
B times A. So we see that the Cartesian product behaves just like our familiar numerical product, but with respect to set equivalence, not equality. For example, our symbol b to the power a, by the way, what is b to the power a? By definition, what is it? Let's recall this definition to our mind. What is it? B to the power a.
A set of all functions from A to B.
Yeah, it is a set of all functions from A to B, and we know that this symbol is indeed similar to exponentiation. For example, if you have C to the power B to the power A, this set is equivalent to which one?
To C to the power B cross A.
And what if you have something like that? C to the power A multiplied by C to the power B. What is it? Do we have any equation for this set?
C to the power A plus B.
But what is A plus B? So in fact, there is. Excuse me, we have some background noise which is intolerable. Okay, thank you. In fact, it is possible to find a similar equation for this case, but we haven't considered that. We have considered this one, A times B to the power C. This is equivalent to what?
A to the power C cross B to the power C.
And here it is an exercise. Here it is an exercise. We haven't proved it. We have indeed A. We have indeed C to the power A, but not plus, but union B. But under some condition, if A and B are disjoint, if these two sets are disjoint, then in fact every function, let me make a drawing illustrating this situation. So here we have something like that, A, B, and we have the set of all functions from A, from the union of these two sets to C. But clearly every such function, given A and B are disjoint, every such function can be expressed as a pair of two functions, a function from A and a function from B to C. Is it clear?
Yes.
It is an exercise, so you can prove it. Okay, what else? We know that, by the way, we have defined some very important family of sets, namely n underlined, where n is a natural number. N underlined was what?
Set of all naturals less than n.
Exactly. It is a set of first n naturals, or equivalently all natural numbers which are less than n. Clearly, if n is greater than 0, it is a set of 0, 1, 2, and so on, up to n minus 1. And these sets serve as our exemplary finite sets. You will see it for yourself, in fact. What do we know about these sets? We had a very interesting theorem which relates this symbol, something to power something, with the power set. We proved the following. The power set of A is equivalent to what? To which set? For every A, the power set of A is equivalent to
2 underlined and power a.
Yeah, 2 to the power A, of course. But and this set is quite interesting. What is it? It is a set of all functions which are defined over A, functions from A to 2 underlined. And 2 underlined is a set of two elements. It is our exemplary two-element set. So this is a set of all functions which are defined on A and take either 1 or 0 as their values. And clearly, you can consider only such points. You can consider the set of all such points here where our function takes value 1. Of course, everywhere else it takes value 0. And clearly, every such function from A to underlined, it can be naturally mapped to some subset, namely the set of all elements where it takes value 1. And vice versa, for every subset, you can consider a function which takes value 1 exactly at this subset. Is it clear?
Yes, it's clear.
And this function is called a function that takes 1 if and only if our element belongs to some fixed subset X. So this function is called the indicator function of this set. And we saw last time that those indicator functions they allow us to replace set theoretical arguments by purely arithmetical arguments, by counting something, opening brackets, and doing things like that. And as a result of the previous lecture was the following one. What if we consider functions not from A to underlined, but from n underlined to A? These are interesting functions. A is some arbitrary set, whatever, while n underlined is, of course, a set of exactly n elements. all naturals starting from 0 up to n minus 1. So we have such a function with a finite domain. So what do we know about such functions? Functions over a finite domain. What was the theorem we proved last time? Was anybody present then? Ladies and gentlemen, are you here?
Yeah.
But you just do not remember. It's a shame. So the theorem was as follows. This set is equivalent to this one. This result is very easy, and maybe you think that it is tedious, it is trivial or something like that. No, it is, of course, quite formal, but it is very important. What does it mean? It means if you have a function, if f is an element of this set, that means that f is a function from n underlined to a. Every such function can be encoded by a tuple. So here leave the functions of this form from n underlined to a. I hope it is quite clear. But who dwell here? Which objects? What is a to the power n? What is it? The Cartesian power. A times a and so on times a n times. What is it? It is a set of all tuples. It is a set of all tuples of length n, where every coordinate of such a tuple belongs to a. Do you remember that?
Yes.
So that means that there is a one-to-one correspondence, a bijection, between finite domain functions and tuples. And the idea of this correspondence is very obvious indeed. You can construct such correspondence phi the following way. You map every function f to what? To the tuple of its consecutive values, f of 0, f of 1, and so on up to f of n minus 1. Is it clear?
Yes.
You can describe every such function. You can encode it by a one-to-one correspondence with a tuple of its values, and vice versa. Of course, given a tuple, you can construct a function whose value at 0 is a0, whose value at a1 is at 1 is a1, and so on. So we have a natural bijection between finite domain functions and tuples. So effectively, we have, say, two ways to describe a tuple of two elements, a pair. One way is our usual way from set theory, where we are considering an ordered pair of A and B. Please stop this background noise, or otherwise I have to find the perpetrator and mute you. Okay, thank you. And another way to describe this pair is this one. You can consider A and pair it with 0. You can consider B and pair it with 1. Of course, both ways require pairing, so it is not very interesting. But if you are considering, say, triplets, for triplets, you can describe a triplet alternatively. You can just pair every coordinate with its number. 0 and A, 1 and B, 2 and C. This is another way to describe this finite sequence, this tuple of elements, this ordered tuple of elements. Is it clear?
Yes.
Okay, and now let us move on. Our next topic is so-called embeddings. What is an embedding? An embedding, you know, informally, set equivalence. By the way, set equivalence, we introduced it in order to capture the notion of two sets of equal sizes, of two sets which have the same size, the same number of elements. This was our model, our formalization for the intuition of the same size. Two sets are of the same size. We say if and only if they have, there is a bijection between them. And we proved that this concept of set equivalence behaves that way, exactly that way we could expect from our intuitive notion of the same size. Say, we proved that A and A are of the same size, they're equivalent. If A is equivalent to B, then B is equivalent to A. If A is equivalent to B and B is equivalent to C, then what?
And A is equivalent to C.
Yeah, A is equivalent to C. These properties are natural, for they are expectable from the concept of two sets of the same size. And our formal notion of equivalence is up to this point in a good accord with the informal notion of two sets of the same size. Informally, that means that A and B has the same number of elements. They are of the same size. But okay, set equivalence means that they are of the same size. But what if we want to say that one set is greater in size than the other one? What is the formal equivalent, formal analog of the following idea? Say B has no less, greater or equal, that is, no less elements. B has no less elements than A. What? How can we formalize it? Do you have any idea? B is greater or equal than A in size. They are of the same size. We formalize it by constructing a bijection. But what should we take for as a formal analog of this concept? B has no less elements, greater or equal. Do you have any proposals? Anybody? Please do not hesitate. Hmm? Okay. The main idea is as follows. So, what do we want? We want the following. A, B has no less elements. That is, A has the same size as a part of B. Is it logical in formula?
Yes.
So, how can we formalize it? It is quite clear. It is quite clear how can we formalize it. That is, there exists formally that would mean something like this. The part of B, and of course it is realizable as a subset. There exists a subset C of B such that A is equivalent to C. So A is equivalent. Here we have A. This one is B. There is some C which is equivalent to A. There is a bijection between A and C. They are of the same size, and C is a subset of B. Is it clear?
Yes.
It is logical, but technically, this definition is not very convenient technically. But of course, the definition we will give will be equivalent to this one. Okay, please look at this picture. Here we have a function, a bijection between A and some subset C of B. But do you agree that this f, which is a bijection from A to C, it is also a function from A to B? Do you agree?
Yes.
Is this function a bijection between A and B?
No.
It is not necessary so. Why? What does it lack to be a bijection? What is a bijection? A bijection is a function which is
surjective and injective both.
okay. So, and now let's check whether the f retains any of these two properties. Is it surjective?
No.
No, it can be not surjective for B. Why? Because all its values belong to C, and it is well possible that B has some element which doesn't belong to C. So it is not necessarily surjective, but is it necessarily injective?
Yes.
Of course, as a function from A to C, it has no such situations, no arrows with distinct beginnings, but the same ending point. This situation is not possible. And of course, if we look at the same f, the same set of pairs as a function from A to B, we still have no such situation. Of course, it is still injective. So f is an injection from A to B. F is an injection. F is an injection. Okay. So this will be the base for our definition. I say that by definition, A is embeddable into B I will use this symbol, which of course, which is similar to less or equal, which is similar in appearance to less or equal, and of course this symbol is it is meant to denote this concept of A has less or equal number of elements than B. A is embeddable. It is read the following way. A is embeddable. Is embeddable. There is an embedding. It is embeddable into B. There is an embedding. If and only if there is an injection, not necessarily surjective, but an injective function from A to B. Is it clear?
Yes.
And this very notion, this very concept will be our formal translation, our formal analog to the informal notion that A is less or equal than B in size. That means that there is a bijection. Okay, and now let us look at a few examples. First of all, our first example, if A is a subset of B, then A is always embeddable into B. Why is it so? If it is a subset, by the way, we will use the following symbol. F, that means that F is an injection. F is an injection from A to B. So it is embeddable, and F is that very embedding. By the way, if A is a subset of B, is there an injective function which maps A to B into B?
Function of pairs AA.
Of course, but what is the name for that function? The identity function, the identity relation, isn't it?
Yep.
The identity relation or the identity function is, of course, injective. So clearly it is a function from A to B, as it is a function from A to A. It takes every element from A and just doesn't change it. It maps it to itself. Still, it is an injection. Distinct elements are mapped into distinct values. So every subset is embeddable, and it is very, very expectable. Why? Because, of course, if A is a subset, if A is a part of B, clearly A has no more elements than B does. It has no more elements. Okay. What else? Say, I don't know. Let us call, let us consider, say, naturals. N is a set of all naturals, and E, let E be the set of even naturals. Even naturals. Say 0, 2, 4, 6, and so on. Clearly, from our first example, it follows that E is a subset of N, hence, of course, E is embeddable. Is it clear?
Yes.
But is it true that the set of all naturals is embeddable into the set of even naturals? Clearly, it is not a subset. There are naturals which are odd. But is it embeddable?
No.
Really? So assume that we have the set of all naturals. Is it possible to construct an injection from this set to the set of all even numbers? 0, 2, 4, 6, 8.
Yes, it's possible.
How? You map 0 to 0, 1.
To 2, 2 to 4, x to x, and so on.
X to twice x, 3 to 6, 4 to 8, and so on. So our function is something like that. Every x is mapped to twice x. So this function is clearly an injection. Is it clear?
Yes.
So n has no more elements than E. It has no less elements than E, but indeed, of course, they have the same number of elements, but we will discuss this point a little bit later. First, let's prove the following lemma. As usual, I want to prove that my formal notion of embedding satisfies all expectable properties which are natural for its informal counterpart. First of all, of course, every set is embeddable into itself. Every set has no more elements as itself than itself. Is it clear?
Yes.
If A is embeddable into B, if it has no more elements than B does, and B has no more elements than C, then what should it be?
A is embeddable to C.
So we want this, and is it true? Assume that here we have an injection F from A to B, and we have an injection G from B to C. Is it necessarily the fact that the case that we have an injection from A to C?
Yes, their composition.
Their composition we know quite well, or at least we should know that a composition of two injective functions is an injective function. What else? Assume that A and B have the same number of elements, that is, there is a bijection. It should be so that A has no more elements than B. Do you agree?
Yes.
But do we have an injection from A to B?
It's F.
F, of course, is such an injection. And likewise, if they have the same number of elements, it must be so that B has no more elements than A does. Do we have an injection from B to A?
Converse of F.
Yeah, the converse relation to a bijection is a bijection itself, so in particular it is an injection. And the fourth claim of this lemma is that this definition in fact is equivalent to our original intention to say that A is equivalent to some part, some subset of B. We say that A is embeddable into B if and only if there exists some C, which is a subset of B, such that A is equivalent to C. That's it. Okay. Let's prove it. Of course, the first 3 points, I hope they have been already proved. And now let's consider this one. From the left to the right, assume that there is indeed an injection from A to B. There is an injection. What should we take for C?
Range of f.
Range of f. Okay, you can call it the range of f, or beta, it is the image of A under f. As it is, as f is a bijection, you know, every function is surjective for its range. Is it clear?
Yes.
Every function is surjective for its range. Every relation is surjective for its range. Hence, our f is a bijection. It is still injective, of course, and it is surjective for f of A. So it is such a bijection. I hope it is clear. Do you have any questions?
No.
And for the opposite direction, assume that C is given. Assume that we know that A is equivalent to C, where C is a subset of B. Of course, clearly that means that there is some bijection f. F is a function from A to C. It is, of course, a bijective function. F is an injection. It is injective. And of course, being a function from A to C, it is also a function from A to B. Is it clear?
Yes.
Okay. So we have such an interesting concept of embedding. But another important property is expectable from the informal point of view. You know that if x is less for numbers, we know that if x is less or equal than y, and y is less or equal than x, then what holds true?
Then they're equal.
They are equal, of course. We want something alike here. Is it true that if A is embeddable, there is an injection from A to B, and there is an injection from B to A, one injection and some other injection? Is it true that there is a bijection between A and B? You know, clearly it is not necessary that F is surjective. F has no obligation to be a bijection. Likewise, G has no obligation to be a bijection. But is there a bijection between A and B? It is very intuitive to think so, because if A has no more elements than B, and A has no less elements than B, they must have the same number of elements. Is it expectable?
Yep.
So it would be natural, but can we prove it? You have two injections, but why do you have a bijection? Why? How can you construct it? It is interesting that you can do so. It is possible, but it is somewhat technical. The argument is somewhat technical, so I will omit it. I will omit the proof, but nevertheless, I will state the theorem. It is known as Cantor Schroeder Bernstein. Cantor Schroeder Bernstein Theorem, And it says that exactly that. If there is a bijection, if there is an injection, an embedding from A to B, and if there is an embedding from B to A, two embeddings which are probably they are not related to each other, but then necessarily there is a bijection between A and B. Is it clear?
Yes.
And this theorem is very important. This theorem is very important because it simplifies, proving that two sets are equivalent a lot, because in general it is way easier to find two injections than one bijection. Okay. Let's consider some applications of this very important theorem. Okay, the first one will be trivial. So what about proof? Okay, the proof is omitted. We'll just believe this theorem. Okay. Okay. Do you remember the fact that for every set, we should know it, for every set A is not equivalent to the power set of A. Do you remember this fact?
Yes.
It is not possible to have a bijection between P of A and A for whatever set A. Aha! But on the other hand, there is an injection from A to P of A. Please construct this one. Is it possible to injectively map some arbitrary set to the set of its subsets?
We can map each element to its singleton.
Yeah, exactly that. You can map every element to its respective singleton. Of course, this is an injection. This function is injective. Why is it so? It's clear. Assume that f of x equals f of y. Two singletons are equal. If two singletons are equal, then of course you know that every element of one singleton belongs to the other one. X clearly belongs to this singleton, hence x belongs to this singleton, so x equals y. Is it clear?
Yes.
So here you map every element to a one-point, a singleton subset. So of course there are at least as many subsets as there are elements. It is quite clear. But still there is no bijection. What does it mean? In view of our Cantor Schroeder Bernstein Theorem, there is a one-way injection, but no bijection. What does it mean?
It's less.
It is less. Informally, you're right. But formally, what does it mean? What is impossible? One injection exists, but bijection is not possible. That means that there is no injection from P of A to A. Is it clear?
Yes.
Formally, this boils down to the statement: there is no injection from P of A to A. Of course, one can prove it directly that no such injection is possible, but such a proof is somewhat more less intuitive than that I had presented in one of our previous lectures. So there is no embedding, no injection from P of A to A. Informally, that means that P of A is greater than A, strictly greater than A. So informally, that means that P of A is strictly greater than A in size. So we can introduce a new symbol, a new notation for this kind of things. Excuse me, we still receive this background noise, this intolerable background noise. Thank you for switching it off. Okay, we can introduce a new symbol. A here is the same as embeddable, but now let us cross this part, this wave line. Let's cross it out. So A is embeddable into B, but not equivalent to it. That means that A is embeddable to B, but it is not equivalent, or in view of our CSB theorem, it is the same as to say that A is embeddable into B, but B is not embeddable into A. Strictly greater. Is it clear?
Yes.
So we see that for whatever set A, the power set is strictly greater than A. That means that there is no set which is the greatest in size. For every set, there is a strictly greater set. But of course, this application was not interesting. And let me move to more interesting examples. Assume that we are interested in two sets: naturals, integers, and rationals. Clearly, they are included to each other this way. N is included into Z, Z is included into Q. Do you agree?
Yep.
We know quite well that inclusion, of course, means embedding. If it is included, if it is a part, then it has no more elements. So N is embeddable into Z, Z is embeddable into Q, and as a consequence, of course, N is embeddable into Q. Do you agree?
Yes.
But is it true that Q is embeddable into N? How many? So you can rephrase this question. How many rationals are there? Is it true that there is no more rational numbers as there are naturals? What do you think? By the way, as a matter of fact, what do you think? How many rational numbers there are there? How many rational numbers are there? By the way, does everybody know what a rational number is? It is a fraction, a ratio of two naturals or two integers. Is it clear?
Yes, we know it.
So, but how many rationals do you have? It is a very natural question.
Infinitely many.
But there are different infinities. You know, for every set, its power set is strictly greater. So if you take an infinite set A, then its power set is even more infinite. It is still infinite, but greater than. All this business is necessary to compare infinite sets in size. It is not the case that everything beyond finite sets is infinite and equivalent to each other. No way. There are many distinct infinities. But what can you say about Q? Apparently nothing. But nevertheless, this set Q is embeddable into N. And in view of our CSB theorem, Cantor Schroeder Bernstein Theorem, it is equivalent to N. Okay, let me prove this fact. Let's consider rational number, say 2/3. Are you familiar with this rational number? What does it mean? That. Are you familiar or not?
Yes, we're familiar, I think.
You are. And what do you think about another rational? Say 4/6. What is it? Is it something else or the same number?
It's the same.
Yes, it is the same number, but another name for the same number. But can we prefer one between? Of course, there are many more such numbers. Say 10/15 or something like that. I don't know, 14/21.
Yeah, it's the same.
They are the same, but can we prefer one among them?
Usually we choose 2/3 because it's you can't divide it by.
Yeah, this is known as an irreducible fraction. Do you know this term?
Now, yes.
Irreducible means that the greatest common divisor of the denominator and numerator is 1. They are co-prime. By the way, have you had co-prime numbers in your number theory course?
Yes.
So it is irreducible. That means that you have already cancelled out everything what was possible from the numerator and the denominator. It is an irreducible fraction. And the main idea is that you can map every rational number. You can map, okay, let's write down something like that. For every rational number Q, there exists a unique irreducible fraction representing it. It is somewhat informal, but I hope it is comprehensible. Is it clear? There is just one irreducible expression.
Yeah, it's clear.
Okay. And as an exercise, let's consider something like that. I don't know. Minus 0.125. Is it a rational number? Of course it is. Minus
Yeah, it can be.
125 over 1000. But what is the irreducible expression?
-1 over 8.
Of course. Of course. This one is irreducible. Is it clear?
Yeah, it's clear.
And what if you consider, say, something integer, say 5? What is the irreducible fraction for 5?
5 over 1.
Exactly. What else? But more complicated question. For 0, what is the irreducible expression for 0?
0 over 1.
Yes, 0 over 1. Why 1? Because the greatest common divisor of 0 and 1 is 1. And if you take, say, 2, 0 and 2, then, of course, the greatest common divisor will be 2, because 2 divides 0. 0 is divisible by 2. Do you agree?
Yes, but
Do you have any doubts that 0 is divisible by 2? 0 equals 2 multiplied by 0.
yeah.
So,
can we write any irreducible type?
Irreducible what? 0 over 1 is an irreducible fraction.
0 over 2.
0 over 2 is reducible because you can divide both. You can divide both the numerator and denominator by 2.
Yeah, okay.
You can cancel 2 out here.
Yeah, okay. Thanks.
And here you can cancel nothing. Formally, this everything here boils down to computing the greatest common divisor. So formally, you say that a fraction is irreducible when the greatest common divisor of its numerator and denominator equals 1. So, and now we will define the following function. This function f takes a rational number and maps it to 3 naturals, to a triplet of naturals, It takes one rational and maps it to a triplet. It proceeds the following way. F of q equals what? It will equal m, comma, n, comma, say 1. It doesn't matter whether it is 1 or I don't know. If q equals m over n, where m and n are where n is positive, m is positive or 0, and of course this expression this fraction is irreducible. And if q equals minus m over n, for the same, it will be m n and say, I don't know, 2. Is this idea clear? Okay, let us try. Minus 3 over 6. What is it?
minus 1 over 2.
Of course, but what is the value of our function? This is, of course, minus 1 over
Okay.
2. One,
1, 2, 2.
1, 2, 2. 2 is for sine. And say 4 over 8. What is it? It is still 1, 2, but here we have 1 because it is positive. Is it clear?
Yeah.
But the case for 0 is special. Why? Because you know 0 equals minus 0. So what is f of 0? It can be either 0, 1, 1 or 0, 1, 2. So let's treat it specially. Let's think that 0 is positive. Excuse me, 1. Is this idea clear?
Yes, that's clear.
So we map every rational number to a triplet of its. First of all, we take the irreducible fraction for this Q. Then we consider the triplet whose first coordinate is the numerator of that irreducible fraction. The second coordinate is the denominator thereof. And the third coordinate is either 1 or 2 depending on the sign. Is that idea clear? Is it clear?
Yes.
I think yes.
Do you agree that f is injective? Of course. Of course. Why is it so? Assume that f of q equals f of q prime. So here we have m, n, and I don't know, l. And here we have m prime, n prime, l prime. But by definition of our function, that means that q equals what? Q equals m over n multiplied by the sign. The sign is what? It is either plus or minus. So it is plus if here we have 1, and it is minus if here we have 2. So it is minus 1 to the power L plus 1. You can arithmetically express it this way. Is it clear? Or no? Yeah, exactly, this way. And likewise, q prime is m prime over n prime multiplied by minus 1 to the power L prime plus 1. Is it clear? But it is given that these triplets are equal to each other. That means that m equals m prime, n equals n prime, L equals L prime. And of course, then q equals q prime. Isn't it clear?
Yeah, it's clear. So it's injective.
Yeah. We have an injection where from? From the set of all rationals to the set of all triplets of natural numbers. Please notice that it is not a surjection. For example, everywhere m and n are co-prime. Their greatest common divisor is 1. So it is not possible to have, say, 2 and 4 here as the value of our function. It is just an injection. But it proves to be enough. This suffices. So we know now that Q is embeddable. There is an injection into n to the power 3. Do you agree?
Yes.
I'm not sure. Can you write it step by step?
What is the problem? We have mapped every rational number to a triplet.
Yeah, okay.
Of course, we haven't used every triplet, but it was not necessary. It is an injection, but not a bijection. Is it clear?
Yes.
What is n cubed? N cubed is n squared times n. But we know quite well that this is equivalent to n. So this product is equivalent to n times n, which is equivalent to n. What do we have? We have that q is embeddable into n cubed, while n cubed is equivalent to n. But if it is equivalent, it is of course embeddable. So we see that q is embeddable into n. Do you agree?
Yes.
Let us come back a few steps. We know that n is embeddable into z, z is embeddable into q, and now q is embeddable into n. So we have the following chain of inequalities, n or embeddings. N is embeddable into z, z is embeddable into q, q is embeddable into n. Do you agree?
Yes.
But what does our Cantor Schroeder Bernstein Theorem says? It says that if A is embeddable into B and B is embeddable into A, if two sets are mutually embeddable, they are equivalent. They are equivalent. So what does it mean? That means that N is equivalent to Q, because we have two embeddings from n to q and from q to n. And likewise, the set of all integers is embeddable into q and vice versa. That means that these three sets are of equal size. They are equivalent to each other. We have proved it without providing direct bijections, without providing explicit bijections. Is it clear?
It's clear.
And now let's introduce some terminology. We say that a set A is called countable. It is countable, from the word count, to count something. Countable. A is countable. That means that A is equivalent to the set of all naturals. Sometimes they also call finite sets countable, but we don't want to do that. Don't want to do that. A set A is countable if and only if it is equivalent to the set of all naturals. So now we see that Q and Z are countable sets. Is it clear?
Yes.
Do you know any uncountable set? Do you have any result that says that something is not equivalent to something?
Power set of naturals.
Yes. For no A is equivalent to its power set. So of course, by the way, there is just single R in the word corollary. By the way, P of n is not countable, or as they say, it is uncountable. It is uncountable. The set of all subsets of naturals is not countable, for it is not equivalent, as we know, to the set of all naturals. But this set is of some interest. By the way, have you discussed cardinalities, the number of elements in your calculus course?
I think no.
By the way,
Can you give an example?
what do you have in your calculus course currently? What are you studying?
The limits of function.
What of function?
Limits.
Limits. So something like continuity at a point. Yeah. I see. So, but nevertheless, there is a fact. This fact is based on the definition of real numbers as a set. Of course, this definition is more complicated than that of naturals. So if we have skipped the definition of naturals, of course it is understandable that we will omit the definition of reals. But nevertheless, as a matter of fact, please remember that the set of all reals is equivalent to the set of all subsets of naturals. There are as many real numbers as there are subsets of naturals. So as a corollary, you know, I hope you haven't yet forgotten it, that for every set, its power set is equivalent to 2 to the power a. Do you remember?
Yes.
So as a corollary, the set of all real numbers is equivalent to this set. It is a set of all functions from naturals to zeros and ones. But every such function, what is it? It is a sequence. What is it? It is a set of all functions from naturals to underline. It is a set. It is a set of all sequences of zeros and ones. You know, every such sequence is 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, and so on. Every such sequence is indeed a function. Which one? F of 0, f of 1, f of 2, f of 3. Is it clear?
Yes.
In general, every sequence with natural indices, every such sequence, I'm sure that you have sequences in your calculus course. Have you had sequences?
Yes.
Every sequence is indeed a function, from naturals to some sets, say reals. So here we have that the set of all reals is equivalent to the set of all sequences of zeros and ones, of all such infinite sequences. One interpretation to this fact is as follows. You can express every real number as an infinite fraction but in binary notation. Is this idea clear?
Yep.
But I need these things for the only purpose. I want to prove one inequality. Okay, it won't take much time. 2 to 3 minutes, but this inequality comprises many interesting facts about infinite sets. First of all, do you agree that the set of all reals is equivalent to this set?
Yes.
What do we have here? Here we have pairs x 0 for all real numbers. Clearly, there is a bijection between reals and such pairs. Do you agree?
Yes.
But this set is, of course, a subset of all possible pairs of reals.
It's logical.
It's logical, of course. You know that reals are equivalent to 2 to the power n. Hence, this set is equivalent to this one.
Yes.
But what do we know about the situation a to the power c times b to the power c? What is it? Do you remember?
It's a cross b to the power c.
So it is what? 2 times 2 to the power n. Do you agree?
Yes.
Interesting. What is 2 multiplied by 2?
4.
It is 4. It is this way in elementary arithmetic. But in fact, it is the same in set theory. Or formally, what is it? It is a set of 4 pairs: 0, 0, 0, 1, 1, 0, 1, 1. Do you agree?
Yep.
Clearly, there is a bijection between this set and the set 4 underlined. You can map this pair to 0, this one to 1, this one to 2, this one to 3. So clearly, these two sets are equivalent. 4 underlined and 2 multiplied by 2, they are equivalent. Hence, this set is equivalent to this one. Do you agree?
Yes.
What is it? It is a set of all functions from naturals to numbers 0, 1, 2, 3. By definition, do you remember the definition of the symbol b to the power a? So it is a set of all sequences of zeros, ones, twos, and threes with natural indices. But every such sequence, every such function is a function from naturals to naturals. Do you agree?
Yes.
But every natural number is a real number. Every natural number is a real number, isn't it?
Yes.
So every sequence of naturals is a sequence of reals. But the set of reals is equivalent to 2 to the power n. Hence, this thing is equivalent to 2 to the power n to the power n. What do you know about this situation?
Then it's 2 to the power n cross n.
Exactly. Exactly. What do you know about n cross n? What is it? N multiplied by n.
Equivalent to n.
Yeah. So this thing is equivalent to 2 to the power n, that is to r. Wonderful. But of course, we know that if something is equivalent, then it is embeddable. If it is a subset, it is still embeddable. Do you agree?
Yes.
And what do we have here? We see that every and each set in this chain, has no less elements than R and no more elements than R has. Is it clear?
Yes.
Every set here is embeddable into the set of reals, and the set of reals is embeddable into every set in this chain. So what do we have? We have that the set of all reals is embeddable into the set reals times reals, and this one is embeddable into R. And the same for the set n to the power n, the set of all functions from naturals to naturals. The same for r to the power n, the set of all functions from naturals to reals. All these sets are mutually embeddable with R, and by our Cantor Schroeder Bernstein Theorem, that means that all these sets are equivalent to R and to each other. Isn't it interesting? What do you think? So, let's look at some informal interpretations. How many points on the plane do you have? How many plane points do you have?
Infinity.
The same? Oh no. There are many distinct infinities. There is no such object as infinity. We have as many points on the plane as we have on the line. R times R, the plane, the set of all plane points is equivalent to just R. Isn't it interesting? George Cantor once remarked about something like that. I see it, but I don't believe it. There are as many points on the plane as there are points on the line. There is a bijection between the two. There are as many, how many functions from naturals to naturals do we have? As many as we have real numbers. How many functions from naturals to reals do we have? How many sequences of reals do we have? In fact, as many sequences as we have real numbers. So probably you need some time to digest these facts, think of them. So please do not forget this proof. Think about it. And I hope you will have some support for your efforts during your seminar classes, where you will solve problems concerning these topics. Do you have any questions?